Good. So the motivation for my talk today, similar to the previous talks in this session, is a setting where we have users with potentially sensitive data. And we would like to run a statistical analysis, like a summation or an aggregation or a machine learning procedure on the data while protecting the user privacy. In particular, we want differential privacy, although that won't be, as you'll see, the focus of the talk. I won't talk much about differential privacy in the talk, but that's what we would like to get. And when we're after this kind of privacy-preserving aggregation, machine learning, summation, there are different trust models, as you saw in the previous talks in the session. We can talk about a trusted curator, about the local model where users don't place any trust in the aggregator or the curator of the data, or about distributed trust settings, which is what I will focus on today. So I'll define that. I'll go into more details about that. But before then, I want to really pin down the task that will be of interest today, and that task is vector summation. Okay, so we have n clients, these beautiful devices, with each of them has a data vector. The vector is a real valued vector in high dimension. Okay? And you should think of the norm of the vector as being bounded. For the sake of simplicity, let's say that the L2 norm is bounded, so the sum of the squares of the entries in the vector is at most 1. Okay, and the goal is to output the sum or the average of all of these vectors. That's the goal in the talk today, just summation. And this is a very important subroutine. One main motivation for us in working on this is gradient descent, where you can think of these devices as containing the gradients of different users. Those are real valued vectors in nowadays in very high dimension. And in a step of gradient descent, we want to compute the sum or the average of the gradients of many users. And we want to do it in a privacy preserving way. So that's the task for today, vector summation. And then I promised I would tell you more about the trust model. So the trust model today is what's known today as the PRIO, or distributed trust model, where we have 2 servers, and we assume that at least one of the servers is being honest, so the servers are not colluding, and one of them is, at least one of them is honest in protecting, following the protocol as it should. Okay? And now the clients interact with the servers in a very particular way. Each client it has its input xi, it sends contributions or messages to the 2 servers, separate messages to the separate, it has a private channel with each of the servers, and this is done by each of the clients on their own. The clients don't interact with each other, they don't communicate, they don't need to wait for each other. And the servers can communicate, they don't trust each other, or they don't collude with each other, but they can communicate, and in the end they should output a good approximation. I didn't say it, but I'm not after, because I want differential privacy, I don't want the exact sum of the vectors. I'm willing to tolerate some small error, some small L2 error. Okay, so that's the trust model for today. And I want to tell you a little bit about how kind of the structure of protocols that a lot of previous works have used before telling you about our contributions. Okay, so in the PRIO work of Kurrigan, Gibbs, and Bonnet, they tackle, this was one of the important functionalities that they talked about. And the idea in the PRIO protocol and in many protocols that followed it is we have inputs, they are real valued vectors, but real valued vectors, since we have finite precision, can easily be transformed into integers, right? We just blow up the magnitude of the vector, and now we have an integer instead. We just scale things up, so we have integers. And now the arithmetic, in order to do secret sharing and protect privacy, we do the arithmetic not over the integers when we're talking about summation, but we do it modulo some prime, so the addition is being done, or many of the operations are done over a finite field of prime order. Okay? And what the users do is each user secret shares its input, so it secret shares each coordinate of its input, which is now a field element, as 2 field elements being sent to the 2 different servers. Each server gets a uniformly random field element, so its view, it learns nothing, but the sum of these 2 field elements, u and w, equals the x that is being shared. Okay? So long as the servers don't communicate or collude, so far they have learned nothing, but using linearity, this is very conducive to computing sums. So in order to recover the sum of many contributions from clients, each server can sum its own shares on its own without communicating with the other server. Now notice that once, now we have to go through all the animations again, sorry. So each server can sum its shares on its own, Because of linearity, once they sum their shares, the sum of the shares of each server is actually a secret sharing of the correct sum of all the user contributions. So if we weren't concerned with differential privacy, they could just share the sum of shares with each other. Since we want differential privacy, each server adds a little bit of noise to its sum of shares, and now the servers can exchange their noisy sums, recover the noisy sum of all the client contributions, and that's a good approximation to the sum of the vectors. Okay? And addition here is being done coordinate-wise. Everything is done coordinate-wise. Okay, so that's a really nice protocol. Why am I giving a talk? I'm giving a talk because there are concerns with the protocol, and one particular concern, which was referred to as robustness in previous talks, I'm going to call it poisoning attacks, is that we don't necessarily trust the client. So some client could be coming online trying to attack our system. In particular, a really effective attack here would be contributing a giant vector that just totally overwhelms the sum and completely throws off our machine learning. Okay, so there are many different types of poisoning attacks one can consider. We focus on the attack, which is a serious, very concerning attack, of just like malicious clients contributing huge vectors. Okay? So we don't want to allow that. We want to catch any poisoning. So if a client is trying to contribute a vector whose sum of squares is too large, we want to catch that. But of course, we also want to maintain privacy. So we can't just look inside the client's vectors and see that the magnitude is too large. That would require looking at the vector of the client, which we want to avoid. So what we want to do is what's known today as a distributed zero-knowledge proof. A protocol where the client can prove that the sum of squares of its vectors entries is small, in such a way that if the sum of squares is small and the client honestly follows the protocol, nothing or almost nothing is revealed. Whereas if the client is lying, if the sum of squares is larger by any amount in the bound that we allow, the servers will catch this with high probability and simply throw away that contribution. Okay? So now the idea is that the clients, in addition to their secret share, each client will add a small proof, a little proof is sent to the first server and a small proof is sent to the second server, and then the servers can communicate with each other in order to verify the proof, and there we go, we've managed to prevent hopefully these poisoning attacks. Okay? So I want to focus on a particular type of proof system, or two different parts of a proof system for this task. And the first one, many protocols have this structure. One thing we start out by checking, including our protocol, is that the sum, okay, so I want to say there's a change in notation here. I didn't want to have two subscripts. So now I'm just talking about one client. Okay, so the client's vector is x, and x sub j is just the jth coordinate of x. And we can forget about the fact that there are n clients. We just want to verify one client's contribution. Okay? So the protocol runs two checks. The first is to verify that when we compute the sum of the squares over the field that we're in, that is small. Okay, that result is small. And that we can do using very beautiful protocols, starting with the work on linear PCP-based protocols of Bonnet et al. They're efficient, lightweight, relatively lightweight protocols for this. So that's very nice, but of course it's not sufficient. Right? So the sum of these, there are many entries, the vector has huge dimension. The sum of the squares could be small modulo q over the field, but as an integer it could be very large. So you could have a huge vector that when you sum it up and take it mod q, you get the answer 0. Right? It's a multiple of q. But the vector itself has huge entries, so that's certainly not enough. The second thing we want to check is that there's no wraparound, that when we compute the sum of squares of the vector over the integers, the result is not larger than q. And if we can guarantee these two properties, then we've satisfied what we want, and we can go home happy. Okay? So the first task, verifying the sum of squares modulo q, previous work did that beautifully. We don't change that much. I don't want to talk about it. I want to talk about the wraparound check. That's the main novelty in our work. Prior work did this by essentially having the client secret share the bit representation of every entry of its vector. Okay, and then they had a protocol for verifying that there's no then they could verify that there's no wraparound, but this is very expensive. In particular, it requires the client to send at least one and actually multiple field elements for every dimension of the vector. That's a big overhead that we want to avoid. So the way we do that is using a novel protocol. That's our main contribution. And in our protocol, the servers send a challenge or present the client with a challenge, a random vector. Each coordinate of it is either -1, 0, or 1. This can be compressed, so sending it doesn't require a lot of communication. And then all they need to check is that the sum of this random vector is z, and the sum of zj, xj over the field modulo q is small. So we said checking sums over the field is easy. We can do that. And we actually show that that's enough. Okay, once you randomize the sum, this randomized check is enough, and we prove that using a case analysis. Two cases, if there are no entries in the vector x that are too large, if all the entries are moderate, or there's no small collection of large entries, then the randomized sum will sort of look like a Gaussian distribution. It will be anti-concentrated, and if it's large over the integers, it will not be small over modulo the prime q, except with small probability. If we do have large entries in the xj, then we can't certainly, if we have one huge entry, then the sum will not look like a Gaussian, but with probability a half, we'll catch such a cheating client because the randomized sum can't be small both with the huge entry and without the huge entry. Okay. So in the second case, we have a probability of a half of catching a cheating client, and we can repeat the check in order to amplify the probability. I want to say that there's a small chance of an honest client failing here. We're not so worried about that. You know, if we drop 1 out of a million clients from our machine learning, that's okay, but it does entail a small, negligible zero knowledge error, so I'm mentioning that. To summarize, that's our main contribution in the new protocol. The main savings is in communication as the dimension d grows. So in this table, you have the different columns from left to right. We have growing dimensionality of the data. In modern machine learning settings, the data is quite high dimensional. In the first row, we have just the communication needed to send the secret shares with no proof, so a system that's totally vulnerable to poisoning attacks. And in the second row, we have our overhead on top of that, so the overhead of our proof over having no proof, and you can see that that becomes really minimal as the dimension, especially as the dimensionality grows, and it's several of orders of magnitude improved over prior work, where each bit of the representation of the entries had to be secret shared. Okay, so this is my last slide. I'm going to summarize. We're in this trust model where we have two servers. We trust that at least one of them has not been corrupted. We're worried about poisoning attacks, and we want distributed zero-knowledge proofs in order to catch those. Our work, the main contribution, is a new low-overhead distributed zero-knowledge proof that a vector has bounded L2 norm. The main savings is that we don't send new shares per coordinate in the client's contribution vectors. And I will end here. Thank you.